afternoon, dear students. In this time, we are going to speak about machine learning, dimensionality reduction. We're going to explore this by analyzing concepts, and after we're going to develop an exercise using Colab. Okay. Why are interventions? Imagine you have survey questions, but only 10 actually matter. Dimensionality reduction helps you focus on what is important, really important. Real world analog, like packing a suitcase. Put in your mind that you are packing a suitcase. Keep essentials, important features, remove duplicates, redundant items, and so on. Benefits: faster models, less storage, and easier visualization. Types of dimensionality. First of all, feature selection. We choose important features, example, correlation analysis. Okay. And second, create new features, example, PCA, TCNA. So, principal component analysis is the VIP section of your data. Here we have a question for the students. When you use a principal component analysis for a data set of 1,000 columns or for 10 columns, you use PCA or for a data set of 10 columns. Analyze it. Okay. Right. It's 1,000. It's for high dimension data. Okay. Let's take a look at our exercise. I have called in-depth principal component analysis. This chapter will explore what is perhaps one of the most broadly used and supervised algorithms. Principal component analysis is fundamentally a dimensional reduction algorithm, but it can also be useful for tool for visualization, noise filtering, feature extraction, and engineering, and much more. After brief conceptual discussion, PCA algorithm, we will explore a couple of examples of these further applications. With the standard by we have matplotlib, and we have update versions of it. Principal component analysis is a fast and flexible unsupervised method for dimensionality reduction in data, which we saw briefly in different aspects. For example, resolution cycle. Its behavior is easy to visualize by looking at a two-dimensional data set. Consider these 200 points in the figure. Let's scatter this. This representation is scattered. We have over here. By eye, it's clear that there is a nearly relationship between X variable and y variables. This reminiscence for linear regression data explore. The probably we explore in linear regression. But the problem setting here is slightly different rather than attempting to predict the y values from x values. The unsupervised learning problem attempts to learn about the relationship between the x and the y values. In principal component analysis, this relationship is quantified by finding a list of principal axes in the data and using those axes to set the dataset. Using Scikit-learn estimator, we can compute this as follows. Let's run this. So we have two components over here. And the fit learns some quantities from data. Most important, the components are explained variance. PCA components. We print to see what these numbers mean. Let's visualize them as vectors over the input data using components to define the direction of vector and explain variance from define the square length of vector. So we have the figure here. This vector represents the principal axis of the data, and the length of each vector is an indicator of how important the axis is in describing the distribution of the data. Measure variance of the data. Each data point on the principal axis are the principal components of the data, essentially. Now, PCA as dimensional reduction. Using PCA for dimensional reduction involves zeroing out more the smallest principal components, resulting in lower dimensional projection of the data that preserves the maximum that much. This example of use PCAs as the dimensional reduction the shape, shape. Data values to a single dimension and the effect of dimensional reduction, we can perform the inverse transform of this reduced data and plot it with the original data, as we can see in this figure. As you can see, the positions are the original, while the data positions are the projection measure. This makes clear that PCA dimensionality reductions the information of the least important principal axis is removed, leaving only the component of the data with the highest variance. The fraction of variance that is cut out proportional to spread of points about the line formed opposite. Early information is discarded in this reduction of the dimensionality. The dimension that is in some senses good enough to encode the most important relationship between points, despite reducing the number of data features 50% of overall relationship between the data points are most preserved. Another aspect, PCA for visualization handles the usefulness of dimensionality reduction may not entirely apparent in only two dimensions, but it becomes clear when looking at high dimensional data. We'll start by loading the data. We have here the information. Recall the digits dataset consists of 848 pixel images, meaning that they are 64 dimensional. To gain more intuition into relationship between these points, we can use PCA to the project them in manageable number of dimensions. We say 2 dimensions. Now, we can plot the first two principal components for each point above the data and seen in the following figure. Recall these components means the full data is 64-dimensional point cloud, and these points are the projection each data point. Along the direction with the largest variance, essentially, we have found the optimal stretch and rotation of 64-dimensional space that allows us to see the layout data in 2 dimensions. And we have done this in supervised manner, that is, without reference to labels. Using the number of points. A vital part of using PCA is practice is the ability to estimate how many components are needed to describe the data. This can be determined by looking the cumulative explain variance ratio as a function of the number of components. The cumulative number of components. This curve quantifies how much the total 64-dimensionality variance is contained with the first n components. For example, we see that this is data. The first 10 components contains approximately 75% of variance, while you need around 50 components to describe close 100% of variance. This tells us that our two-dimensional projection loses a lot of information, as measured by the explain the variance, and that we need about 10 components to retain 90% of the variance. Looking at this plot of high-dimensional data set can help you understand the level of redundancy present in its feature. PCI as noise filtering, another appliance. PCI can also be used as a filtering approach for noisy data. The idea is that any component variance should be relatively unaffected by the noise. If you resolve the data using the largest subset of principal components, you should be preferentially keeping the signal and throwing out the noise. Let's see how this works. This looks the digit data. First, we plot signal of the input noise. Three examples with the following. Okay, let's see. We have the lobes. Let's add some noise to create a noisy data set and deploy it. Therefore, have this figure with the noise ahead. The visualization makes the presence of this random noise clear. Let's train PCA model on the noisy data, requesting that the projection preserve 50% of the pattern. Here, variance amounts of 12% components of the original 64 original features. Now we compute these comments and then use the inverse of the transformation to reconstruct filtered digits. The following figure shows the results. This signal, preserving noise filtering property, makes PCA a very useful feature selection, for example, rather than training classifier on very high dimensional data. You might instead train classifier on the lower dimensional principal component representation, which will automatically serve to filter out random noise in the inputs. Okay, third example, agent faces. Here we will take a look back of the explore bit on when it into different label phases dataset that may available through cycle. This is extension quite big. So let's take a look at the span because it's a dataset. Random so the PCA it uses a random method to approximate the first and principal components more quickly than the standard approach, and the expense of some accuracy. This trade-off can be useful for high-dimensional data. Here, a dimensional near 3000. We will take a look about the first 150 components. So we have components, random state, solver, randomize. In this case, it can be interesting to visualize this image associated with first several principal components. These components are technically known as eigenvectors. So these type of images are often called eigenfaces. As you can see in the following figure, there are three these. The results are very interesting and give us the insight on how the images vary. For example, the first few agent faces from the top to left seem to be associated with an angle of lighting on the face, and the later principal vectors seem to be picking out certain features such as eyes, nose, and lips. Let's take a look at the cumulative variance of these components and see how much of the data of the information projection is preserved. See the following figure. "150 components were chosen to account over just 90% of variance. That will lead us to believe that using these 150 components, we will recover most of the essential characteristics of the data. To make this more concrete, we can compare the input images with the images reconstructed from these 150 components. So we have hence, but how we produce the top row here shows the put images, while the bottom shows the reconstruction of the images. Just 150 of the 3,000 initial features. The visualization makes clear why PCA feature selection use in-depth support vector machines was so successful, although it reduced the dimensionality of the data by nearly a factor of 20. The project might contain enough information that we might I recognize the application points within 150 dimensional data rather than 3,000 dimensional data we choose. Can be much more efficient classification. Summary. In this section, we explore the use of principal component analysis for dimensionality reduction, visualization of high dimensionality data, noise filtering, and feature selection with high dimensional data. Because of versatility and interpretability, PCI has been shown to be effective in a wide variety of context statistics. If any high-dimensional dataset, I tend to start a PCA in order to visualize the relationship between points and relate with this data to understand the main variance of data as we did with interfaces and understand intrinsic dimensionality by plotting the explained variance ratio. Certainly, PCA is not useful for every high-dimensional data set, but it offers a straightforward and efficient path to gaining insight into high-dimensional data. PCA main weakness, it tends to be highly affected by outliers in the data. It's important to know. For this reason, several robust variants of PCA have been developed, many of which iteratively discard data points that are poorly described by the initial components. Okay, I highly appreciate your opportunity. Thank you very much. I'm always in this position to do my best job in favor of the students.